The normal distribution, z-scores. The empirical rule only applies to data values that are exactly 1, 2, or 3 standard deviations from the mean, meaning it has limitations. For other cases, we can generalize this rule if we know precisely how many standard deviations from the mean a particular data value lies. The standard score, or z-score, represents the number of standard deviations a data value lies from the mean. A z-score of 0 indicates the data value is exactly at the mean, right, or it doesn't deviate from the mean at all. A z-score of 1.5 indicates the data value lies 1.5 standard deviations above the mean. A z-score of negative 2.4 indicates the data value lies 2.4 standard deviations below the mean. Notice the sign of the z-score simply informs us as to whether or not the data value is above or below the mean. Positive z-scores always reference data values above the mean, and negative z-scores always reference data values occurring below the mean. Standard or z-scores follow a specific formula. The z-score is always calculated by taking the data value and subtracting it by the mean and dividing by the standard deviation. When a distribution is approximately bell-shaped or normal, we know from the empirical rule that about 95% of the data falls within 2 standard deviations of the mean. So when the distribution's values are transformed into standard or z-scores, about 95% of the z-scores should fall between negative 2 and positive 2. A z-score outside of this range will occur about 5% of the time. Remember, the total percentage under the curve must be 100%. These values, or these data values that occur outside of that middle 95%, are considered unusual. Once we know the standard score of a data value, the properties of the normal distribution allow us to find its percentile in the distribution. The percentile of a data value is the percentage of all data values in a data set that are less than or equal to it. A data value that lies between 2 percentiles is said to lie in the lower percentile. We can convert standard scores to percentiles with the standard z-score table. Pause the video here and download the z-score table from the handouts in our Moodle class website. We want to be careful. We want to recognize how this table is actually described because there are many z-score tables that can be used. For our specific purposes, we want to recognize that the area under the curve is from the left-hand tail up to the z-score, or up to the actual data value, regardless of whether that z-score is positive or negative. Let's take a closer look at reading the z-score table. To begin reading this table, we want to recognize that the z-scores exist along the first column and the top row. First thing we want to do is read the first column to indicate the ones and tenths position of the z-score that we will eventually calculate. Once we have the first 2 place values of our z-score, we're going to take a look at the appropriate columns to indicate the hundredths position. Let's take a look at an example. Find the area under the curve with a z-score of negative 1.38. First thing we want to do is find negative 1.3 and then slide over our columns to find the hundredths position of 8. Wherever these overlap, that's going to give us the approximate area under the normal distribution curve. So in conclusion, we can see a z-score of negative 1.38 has an approximate area under the curve of 0.0838. We can state then that approximately 8.38% of the data values fall below a z-score of negative 1.38 in the normal distribution. Let's take a look at another example. Find the area under the curve with a z-score of negative 3.04. Once again, we begin by finding negative 3.0 and then slide over our columns to the hundredths position of 0.04. Wherever these two overlap, that is going to give us the approximate area under the curve of our normal distribution. We see then that a z-score of negative 3.04 has an approximate area under the curve of 0.0012. or approximately 0.12% of the data values will fall below a z-score of negative 3.04 in our normal distribution. Let's take a look at an example involving data. The typical home doorway has a height of 80 inches. Because men tend to be taller than women, we will consider only the heights of men. Given that the heights of men are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches, find the percentage of men who can fit through the standard doorway without hitting their heads or bending over. Just like with the empirical rule, we're going to begin our solution with our normal distribution, and we're going to label the mean and all of our standard deviations. The mean, we're told, is 69 inches. To find one standard deviation above the mean, we're going to add 2.8. To find one standard deviation below the mean, we would subtract 2.8. We're going to continue this process to find 3 standard deviations both above and below the mean. We then want to shade in what part of the normal distribution we're actually interested in. Since we're interested in finding the percentage of men less than 80 inches tall, i.e. those that can fit under a standard doorway, we can see that we're interested in almost the entire normal distribution. How do we actually calculate our standard or z-score? Remember, the z-score is always going to be calculated by taking the data value and subtracting the mean and dividing by the standard deviation. So 80 minus 69 divided by 2.8 gives us a z-score of 3.93. Then we're going to look that up in the table in order to see that a z-score of 3.93 has an area under the curve greater than our table. Notice our table only goes up to a z-score of 3.49, which has an approximate area under the curve of 0.9998. We can then conclude that the standard doorway at 80 inches tall will be able to accommodate more than roughly 99.98% of the male population. Let's take a look at another example. The first National Health and Nutrition Exam Survey reported that the average body mass index, or BMI, in the 25 to 39 age group for women was found to be 24 with a standard deviation of 5. What percent of women have BMIs less than 22? Because a BMI of 22 is not a full standard deviation above or below the mean of 24, we need to calculate a standard or z-score. 22 minus 24 divided by 5 leaves me with a z-score of negative 0.40. We can then interpret this z-score by reading the table. A z-score of negative 0.40 has an area under the curve of approximately 0.3446, meaning that approximately 34.46% of women between the ages of 25 to 39 have BMIs less than 22. Standardized scores, or z-scores, are typically used to compare different quantities. Notice the scale or the scoring range for the GRE and MAT are different, so they are not easily compared. By first standardizing these scores, we can then make a legitimate comparison. The GRE and the MAT are tests that graduate schools use to evaluate applicants. GRE scores are normally distributed with a mean of 1,500 and a standard deviation of 300, while the MAT scores are normally distributed with a mean of 50 and a standard deviation of 5. You decide to take both tests. You score 1875 on the GRE and a 57 on the MAT. Which test did you score better? And explain your answer. In order to make a legitimate comparison, remember, we need to calculate how well we did on each test. Meaning, in order to compare these two, let's find the z-scores associated with our scores and then compare the two. On the GRE, again, we scored an 1875. The mean was 1,500 and the standard deviation was 300, meaning our z-score was 1.25. On the MAT, again, we scored a 57. The mean was 50 and the standard deviation is 5, meaning our z-score was 1.40. If we look up each of these on the table, we can then indicate what percentile we actually scored in for each of these exams and then compare the two percentages. On the GRE, a z-score of 1.25 has an approximate area under the curve of 0.8944, indicating that we scored in the 89th percentile, or we scored better than 89% of everyone else on the exam. A z-score of 1.40 has an approximate area under the curve of 0.9192, indicating that we scored in the 91st percentile, or we scored better than 91% of everyone else taking the exam. So in comparison, which exam did we score better on? We scored better on the MAT exam because we scored in the higher percentile.